So lesson 2 is about fractional distillation. Now this is going to follow straight on from lesson 1, obviously, because we established that crude oil was a mixture of saturated hydrocarbons. So it was a mixture of alkanes. And so this ties in with topic 8 when we were talking about separating mixtures. And one of the methods we had for separating mixtures was fractional distillation. Now the property that we used to separate substances using fractional distillation was their boiling point. Okay, so substances that had different boiling points could be separated by fractional distillation. And specifically, fractional distillation was used to separate substances that had quite similar boiling points. Okay, so which makes it perfect for this method, because we're dealing with a mixture of different alkanes. They've all got very, very similar boiling points, but by using fractional distillation, we're going to be able to separate them. So, what we have here is a fractioning column. And it's not hugely different to the fractional distillation you would have seen or that we would have talked about before. Okay, we are still going to heat it to evaporate it, and we're going to have the fractioning column, which is going to get cooler as you go up. The only real difference is when we've done this before, we've just had one column which had one product. Here we've got multiple different substances being separated all at the same time. So this is a fractioning column. So we'll start, at the beginning. The first thing that's going to happen is we need to put crude oil in. Okay, so crude oil goes in, but importantly, it goes through this furnace and is heated. So crude oil is heated to evaporation. So all of the different substances in the crude oil all get heated, all get evaporated. So they enter the fractioning column in the gas state. Okay? Now at the bottom of the column, it's very, very hot. And as you go up the column, it gets cooler. Okay? And we call that a temperature gradient. So there is a temperature gradient from the bottom of the column to the top. It gets cooler. So our crude oil is going to enter, and all of our different alkanes that go in are all going to be in the gas state. Now, depending on the size of those alkanes, because remember they're all saturated hydrocarbons, so they all contain just carbon and hydrogen, they all contain just single bonds. The only actual difference between them is how many carbons do they have in that chain. So the more carbons they have in the chain, the bigger the molecule. The fewer carbons they have in that chain, the smaller the molecule. And again, we refer back to that word molecule. The fact that we're talking about molecules means that we're talking about, covalent bonding, covalent molecules, and we know that they should have weak intermolecular forces. Now, how much energy is required to break that intermolecular force depends on the size of the molecule. So we could assume that these ones at the bottom here are going to be the larger molecules, the ones with more carbons in the chain, because the larger the molecule, the stronger the intermolecular forces between them. And up here, we're going to have our really short alkanes, the ones that are small molecules and have really, really weak intermolecular forces between them. So that's precisely what happens. Now, remember, they're already in the gas state, so they're going to go into the column in their gas state, and then they're going to travel up the column until they reach their boiling point, at which point they will condense. Now it's important to remember that the temperature at which a substance condenses is exactly the same as the temperature at which it evaporates. Let's take water for example. Ice melts at 0 degrees. Water freezes at 0 degrees. So the melting point and freezing point are the same. Water evaporates at 100 degrees. And steam condenses at 100 degrees. So the condensing point and the boiling point are exactly the same. So the crude oil, full of different length alkanes, some short, some long, and the longer ones are going to have higher boiling points because they've got stronger forces of attraction. So they're going to condense at a higher temperature. So they're going to condense down here. So we're going to get long chain alkanes are going to condense at the bottom of the column because they have high boiling points. And at the top, we're going to get our short chain alkanes. and they condense at the top because they have low boiling points. So long chain alkanes condense at the bottom, short chain alkanes condense at the top because of their boiling points. And it's important you remember they are condensing because they're already a gas, they've already been evaporated, they're going to condense at these different levels. And the whole reason that's possible is because of this temperature gradient. The fact that it's hotter at the bottom, cooler at the top, allows them all to condense at different levels and therefore be collected at different levels. So we also need to know what they're being separated into. So we call each one of these levels, we call it a fraction, okay? And we call it a fraction because we're not going to collect particular alkanes. You're going to collect a range of alkanes with similar boiling points. So at the top here, these are the LPGs, okay, which stands for liquid petroleum gases. Okay, now straight away, there's an S on the end, it's plural. We're not talking about one alkane. We're talking about a group of alkanes, all similar numbers of carbons, therefore similar boiling points. So at the top here, we get, roughly speaking, 1 to 4 carbons in their chain. And they will all condense right up here. Well, I say condense actually, these will stay as a gas, so these won't even condense. Down here, we've got naphtha. Now naphtha is used basically in the chemicals industry to make lots of different chemicals. You don't need to know any specifics as to what we use naphtha for, just that we use it in the chemical industry. Here we have petrol, okay, which is approximately sort of 8 to 10 carbons. Again, it's a range. It might have some that are 7, it might have some that are 11, but roughly speaking they all got about 8 or 10. And if you think about it, if you go to the petrol station and you get the fancy petrol, it will say high octane fuel. Okay, octane. Oct for 8, ane, alkane. 8 carbon chain alkanes, okay? So it's quite obvious what we use petrol for. We use it as fuels. LPGs, again, we use as fuels. The gas that comes out of the gas taps here in my lab, the gas that is used in your cookers, the gas that is used in your boilers, the gas that you use for your barbecue, those are liquid petroleum gases. Petrol, obviously fuel in cars. Next here we have kerosene. Okay, and as you can see from the picture, this is going to be fuel for aircraft. Then we have diesel. Now this is approximately sort of 12 to 14 carbons, okay? So you're starting to see more carbons. As we're going down, more carbons in the chain. The chains are getting longer, the molecules are getting longer, which is why their boiling points increase, which is why they condense lower down the column. Then we have lubricating oil, you know, the kind of oil that we put in our car engines. And down here we have what we call fuel oil, which we use in ships as fuel. We combust it as fuel for ships. And then right down here at the bottom, we have bitumen. Okay, and you probably won't have heard of bitumen, but it has roughly 120 carbons in its chain, a huge number of carbons. And we use it, it's a really thick, black, sticky sort of tar, and it's what we use in roads, making tarmac. It's what we use on roofs. Now, I'm sure you've seen, anybody who's got a shed roof, you've probably got that sort of a bitumen roof, which is that black, sticky tar, probably with some sort of gravel stuck with it as well. So that's bitumen. Okay, so what you're going to notice is that at the top here we have the ones you've probably heard of, LPGs, petrol, diesel, you've probably heard of those. You know, they're the ones that are useful as fuels. And down here we have the much longer hydrocarbons. Okay, so just to recap very quickly, the crude oil is heated until it evaporates. It goes into the fractioning column. There's a temperature gradient going from hot to cooler at the top, and the different chains, the different length chains have different boiling points, therefore they condense at different levels, with the short chains condensing at the top and the long chains condensing at the bottom. So very quickly we're just going to flow map that. And it's really important that when we're making flow maps that we try to keep as few boxes as possible. We're trying to summarize the information. So first things first, the crude oil is heated until evaporated. Okay, it enters the fractioning column, which has a temperature gradient. Okay, that's really important. So, we're talking about marks here, heated until it's evaporated into the column which has a temperature gradient. These are key terms that you must talk about. Okay? Different length hydrocarbons have different boiling points. Therefore, condense at different levels, and that wouldn't be possible if it wasn't for the temperature gradient. And again, different hydrocarbons have different boiling points and they condense. So these are key terms you have to make sure you're using. Okay, and then finally we can say short chain hydrocarbons have a low boiling point, therefore condense at the top, and vice versa. So you could say the opposite. You could say that long chain hydrocarbons have high boiling points, therefore condense at the bottom. Okay, again, 1, 2, 3, 4 key points, and you'll find that when they ask you to talk about fractional distillation or separation of crude oil, they will probably give you 4 or 6 marks to do it. But if you just wrote these 4 things, you will get 6 marks if it's a 6-mark question, or 4 marks if it's a 4-mark question. It is that simple. Just make sure you are using this key terminology. And again, flow maps are incredibly useful in science for summarizing a process. And again, you want to try and use as few boxes as possible. I recommend 3 or 4 boxes, and you can summarize almost any process into that. Okay, now the next video is going to be me going through this demonstration here, this practical here. Unfortunately, you're not obviously going to be able to do it, but I'll film myself going through that. So we'll get a results table, and we'll be able to then discuss the properties that we see and the trends we see between short chain and long chain hydrocarbons, and then after that, if you could just have a go at the exam questions. Okay, there's a nice big 6-marker on fractional distillation, which using that flow map you should find incredibly easy to answer, followed by a progress check. Okay, and we will look to get a mark scheme out to you so that you can answer this, mark it, and then get back to us with your scores. Okay, and as with everything, just keep checking Show My Homework. Okay, I'll update this channel regularly. I will update Show My Homework with any resources or any instructions that you're going to need. Just make sure you check in on it regularly so that you don't miss anything. Okay.